Welcome to the Arithmetic Zone, and today we're going to do a lesson on factorials. So what are factorials? Essentially, they refer to the product of all positive integers equal to and less than the given integer, and they are represented by a number and an exclamation point followed immediately after. So right here, we have 5 factorial, and that's equal to the product of all the integers equal to 5 and less than 5. So that's 5, 4, 3, 2, 1. Multiply that all together and you get 120. Likewise, with 4 factorial, it's the same thing, but you start with 4 and then work your way down to 1. Pretty much the same concept for 3 factorial and 2 factorial. 1 factorial is only equal to 1 because there's no other positive integer that's less than 1. You have 0, but, well, 0 is not a positive number, so 1 factorial is just equal to 1. And you may realize that there is a clear-cut pattern here. When you increase the number by 1, you end up taking the product of the new number. So with 2 factorial, I take the previous product and multiply it by 2. With 3 factorial, I take the previous product and multiply it by 3. So if you think about it, I can rewrite this as 2 times 1 factorial, this as 3 times 2 factorial, this as 4 times 3 factorial, and this as 5 times 4 factorial. And this is actually a very important concept because this is how we're going to simplify a lot of factorial expressions. And you may also realize we have 0 factorial, and that's just equal to 1. But why? I mean, that doesn't really make sense. I mean, you would think it's just 0 because, you know, there's nothing really, there's no positive integer that's equal to 0 or less than it. It's just, so would it just be 0 or some other undefined value? Well, no, it's 1. And to understand why it's 1, we have to look at what exactly factorials represent. So on to the next slide. Factorials essentially tell you the number of different ways you can arrange multiple items, and this is called a permutation. And permutations are similar to combinations, but with combinations, the order of the items does not matter. So, to give you an example, let's say I have a red ball and a black ball, right? I have these 2 balls. There would be 2 different ways to arrange this if the order mattered. So I could arrange it like that, with the red ball first and then the black ball, or I could do the red ball second and the black ball first. So 2 different ways to arrange this. That's why 2 factorial is equal to 2. But with combinations, the order doesn't matter, so there would really only just be one way to order this. So technically, if you think about it, you have those combination locks, right? They should really be called permutation locks because the order of the numbers does matter when you're trying to crack the code. So, but we just call them combination locks anyway. I don't know why. But anyway, let's get back to the lesson. Using the concept of permutations, we can think of factorials in this manner. 3 factorial means, which is equal to 6. That means that there's 6 different ways to arrange 3 items, which that would be true. Let's say I have a black ball, a red ball, and then this weird color. Okay, it looks gold. So if I have 3 items, there'd be 6 different ways to order this. This is one way. Another order would be if these 2 are flipped, and this was still the last one. Another way would be if these 2 were in the middle, and these 2 were the first ones. So we just fill out the remaining ones. Alright, so yeah, if you have 3 different items, there'd be 6 different ways to order them. 1, 2, 3, 4, 5, 6. You could order them in this manner. And 2 factorial, there's 2 different ways to arrange 2 items, like I showed right here. 1 factorial, there's only one way to arrange 1 item. If you just have 1 black ball, that's it. And this is essentially why 0 factorial is equal to 1. Because, you know, if you have a data set with no values, there's only one way to order that set of no items. Hence, 0 factorial is equal to 1. Anyway, definitions aside, let's get into problems that actually deal with factorials. So almost all these problems deal with simplifying these fractions. with factorials inside them. So let's look at the first example, 3 factorial over 4 factorial. Let's rewrite this in what they actually represent. 3 factorial is 3 times 2 times 1. Likewise, 4 factorial is 4 times 3 times 2 times 1. And these terms are all being multiplied together. Same with the denominator. So what that means is we can actually cancel out all these terms that appear in both the numerator and denominator. So the 3 2 1s, they all get canceled out. And what you're left with is 1/4. And that would actually be your final answer. Now in number 2, this time we're dealing with variables. But notice the concept is still the same. We have a factorial value in the numerator and then 1 greater than that value for the denominator, just like with number 1. So let's look at this closer. We have 3 factorial over 4 factorial. When the denominator is plus 1 over the numerator, we see that the final answer is equal to 1 over the numerator plus 1. So the final answer for this would be 1 over x plus 1. But how can we prove that? Let's think back to prior where I said that we should think of factorials as the current number multiplied by the previous factorial. So as I said before, 3 factorial is equal to 3 times 2 factorial, and 4 factorial is equal to 4 times 3 factorial. Using that concept, we can rewrite this as x factorial over x plus 1 times x factorial. We can cancel out the x factorials and we're left with 1 over x plus 1. Alright, next example, 7 factorial over 5 factorial. So again, let's use that same concept of rewriting them in this format. So we have, and we want to rewrite it in a way that we can cancel out one of the factorials completely. So 7 factorial is equal to 7 times 6 times 5 factorial. And then we just have 5 factorial in the denominator. So these can cancel out. We're left with 7 times 6 in the numerator, which is just equal to 42. With the next example, we have a multiplication happening with 2 factorials. So 5 factorial over 3 factorial times 4 factorial in the denominator. So again, we want to try to cancel out some of these terms. So 5 factorial is equal to 5 times 4 factorial. And let's just keep the 3 factorial and the 4 factorial the same. We can cancel out the 4 factorial and we're left with 5 over 3 factorial. And because, there's no, when we rewrite 3 factorial, we're not going to get the number 5 in there. What we have to do from here is just simply rewrite this in terms of actual values. So 3 factorial is just 3 times 2, which is 6 times 1, which is still 6. So the final answer for this is going to be 5 over 6. Anyway, moving on to the next column, we have x minus 1 factorial over x plus 1 factorial. This looks complicated, but when you realize this, x minus 1 factorial is simply 2 less than this value right here. So let's rewrite x plus 1 factorial so that we can get this value in there. So we're going to keep x minus 1 factorial as it is. And then we're going to rewrite this one as x plus 1 times x minus 1 factorial. Remember the last term, the most recent term that you write should keep that factorial there, because this is going to continue forever basically, because we don't know what x is. So we can cancel out the x minus 1 factorials and we're left with x plus 1 times x in the denominator. So this is equal to 1 over x times x plus 1. You could distribute this if you want, but I'm not going to. Next we have 3 double factorial. So what's a double factorial? Essentially, nothing too fancy. You just take the first factorial, which would be 3 factorial, and then you take the factorial of that resulting value. So 3 factorial we already went over is equal to 6, but then we have another factorial to deal with. So what is 6 factorial? Well, let's write this one out. We have 6 times 5 times 4 times 3 factorial. 3 factorial we already established is 6. 6 times 5 is 30. 30 times 4 is 120. So 120 times 6 is going to be equal to 720. And that's our final answer. Next, we have another double factorial situation here. We have 0 factorial, which we already said is 1, but we have another factorial. 1 factorial is still equal to 1. So this is just 1 times 2 factorial, which is just equal to 2. So that one turned out to be much simpler than we expected. Now we have this problem. Now this looks very, very difficult at first glance, but when we break it down, it's actually not too bad. So let's deal with one type of these terms first. We have an exponential function going on in the numerator and denominator. So let's deal with that first. So using our law of exponents, we can actually rewrite this 2 to the power of x plus 1 into 2 to the power of x times 2 to the first power. When you multiply two numbers with the same base with an exponent, you can just add them up together like that. So we can rewrite it like this. 2 to the first power is just 2. So let's rewrite that. And when we split up the terms like that, you'll notice that we can actually just get rid of these two terms right off the bat. Now, again, 2 to the first power is just 2, so that's just a constant. We don't really have to do anything with it. Now we have 2x plus 1 factorial all over 2x. So, again, let's use that same concept. So, I'm going to try to give myself more space if possible. So, I'm going to start right here. So, we have a 2 right here. So, 2x plus 1 times 2x factorial. Make sure the whole thing has that factorial around it. And then we're left with just 2x factorial in the denominator. So we can cross these out, and we're left with 2 times 2x plus 1, which if we were to simplify, we would get the final answer of 4x plus 2. So even though we got this disgusting little expression, that wasn't so bad, was it? Anyway, pretty short video, well, at least for my standards, but that's a basic rundown of factorials and how you can simplify them and its applications. So I hope you guys enjoyed this video, and stay tuned for more tutorials in the future. Multiply that all together and you get 120. Likewise, with 4 factorial, it's the same thing, but you start with 4 and then work your way down to 1. And I just realized that is not correct. That's 21.